I'm Radek Palánek. I'm from Masaryk University Brno in Czechia, and I'm honored to be awarded the EDM Test of Time Award for the 2015 paper Metrics for Evaluation of Student Models. Unfortunately, I'm not able to participate in this year's Education Data Mining Conference in Seoul, so I would like to share my reflections on the paper, at least in this form. I will start with the original motivation, how I got to writing the 2015 paper. The motivation came from practical experience. I've been experimenting with skill models for adaptive choice of questions, and I needed to choose one of them for actual application, practical application in the product that we have been developing. Based on my familiarity with the research in EDM conference, I have known that people have been using the root mean square error metric and area under curve metric among other metrics, so I picked these two. For my evaluation, I ran experiments, and I ended up with a different winner with respect to each of these metrics. And now I needed to choose one of the models for the practical application, and I didn't know which one to choose. So I started thinking about which of the metrics is more appropriate for my case. I have tried to find advice in research literature. In EDM, EDM papers, I didn't find much advice, so I looked at different domains like weather forecasting, and based on these experiences, thinking about metrics, looking at their properties, I have ended up writing a summary paper about this issue. So the performance metrics in student modeling are used in a number of ways, particularly for parameter fitting and model comparison, and there are many of them. This is just a sample of some of the metrics that you can meet in research papers. What I mean by performance metric is that these are metrics that help us quantify the quality of predictions. So we observe some outcomes, for example, student answer correctly or incorrectly, or student state, like student is bored or is not bored, and we have some model which provides predictions of the state. The outcomes in general can be of various forms: binary, multi-class, or even continuous. In the case of student modeling, most often we work with binary outcomes: correct, incorrect answer, student state is bored, is not bored, and the predictions are numbers between 0 and 1. In the paper, I provided a division of the different classification of different metrics into 3 types: probabilistic understanding of errors, qualitative understanding of errors, and ranking of examples. With probabilistic understanding of errors, we understand the predictions as probabilities and treat them as such, for example, using the local likelihood method, or another typical choice of this type is root mean square error metric. With qualitative understanding of errors, we apply some threshold to the predictions, so we end up with binary predictions. So we have binary predictions and binary outcomes. Based on these, we construct a confusion matrix, and based on the values in the confusion matrix, we can compute unidimensional metrics like accuracy, precision, recall, or their combination. And the third type of metrics is exemplified by the area under receiver operating curve metric. Here we focus on relative ranking of predictions. The receiver operating characteristic curve is given by plotting false positive rate on one axis, true positive rate on another axis. For each possible choice of threshold, we get different combination, and the area under curve summarizes the whole curve. In the 2015 paper, I provide some arguments about the natural mapping, in my opinion, natural mapping between different uses of models and different metrics. I argue that for skill modeling, where we are trying to predict the correctness of next answer, natural choice is one of the metrics with probabilistic understanding of errors, right, root mean square error. For affect and motivation, where the models try to predict the student state, like bored or confused, it seems natural to use qualitative understanding of errors with binary predictions. And I also provided some arguments why the area under curve metric, which has been traditionally used quite a lot for student modeling, is actually not a natural adapt for the models, And also I provided some arguments based on the literature from other domains why the area under curve may not be a really suitable metric. So the main summary of the 2015 paper was one technical point was concerned with mean absolute error, a specific metric which has been used in several research papers, but I provided specific technical arguments why for binary outcomes it can be misleading and provide completely wrong conclusions in some cases. So I provided some technical arguments why mean absolute error should not be used. With respect to area under curve, the situation is more complex. Here I provided some arguments, partially subjective, why I believe it is overused and should be used more carefully. And my recommendation was to use as a default metric root mean square error. But the more important high-level point was that the choice of metric deserves more attention that is currently getting, and that other domains can provide useful inspirations, particularly, for example, weather forecasting, where they have been doing probabilistic predictions for a long time, and they have thought about evaluation quite a lot. In the following years, I continued some of this line of research. The most of it was written down in a journal paper in user modeling and user interaction in 2018, which dealt with other methodological nuances in the evaluation of student models. The paper dealt with several of them, for example, with attrition bias and such things. Here I would want to highlight two of the issues discussed in this paper: averaging in metrics computation, which directly follows up on the basic overview of metrics, and then with issues about cross-validation and data splitting. Concerning averaging, the discussion so far concerned global computation of the metrics, but in student modeling, the data have some structure. We have students who are answering items divided into some knowledge components. And the basic computation of performance metrics just ignores these structures and treats all predictions and observations as the same. But we can also pick individual students, compute root mean square error for individual predictions for individual student, and then average these predictions. Or we can take knowledge component, take all predictions for these knowledge components, compute quality of root mean square error for this knowledge component, and then compute average across knowledge components. Each of these approaches effectively gives different weights to different observations. None of them is inherently correct. Each of them has different advantages and disadvantages and different uses. And each of the important point is that each of them can lead to different numerical results and also to different comparison of models. In the follow-up journal paper, I provided some specific situations illustrating how the choice of the averaging can influence the comparison of models. And this seems like a nuanced point. Often this issue is not properly reported in research papers, and yet it can have non-trivial effect on the results of evaluation. Something similar happens with respect to data splitting. In the evaluation of models, we typically divide the data into training set and test set, and this division can be done in different ways. The simplest is an uniform division where we just randomly divide the data into training and testing set, but we can also respect the structure of underlying data. So for example, we can care about generalization of the model to new students or new student populations. So in this case, we may split the data, we may use student level stratification, where some students are completely in the training set and some students are completely in the test set. Or some student subpopulation is completely in the test set. Or we can be interested in generalization with respect to new items or new knowledge components, and in that case we put some items completely into the training set and some items or some knowledge components completely into the test set. Various researchers have used various approaches. Some papers report which of these have they used. Some papers even do not report what approach they are using, which complicates their application. We have to guess whether they have used uniform division or some other kind of stratification. And again, these choices may non-trivially influence the results of evaluation. Another aspect of the cross-validation methodology is whether the predictions are updated dynamically or they are treated statically. The simple approach is that you take the train set, train the model, and then compute all the predictions for the test set based on the train set, the trained model. More realistic to practical applications are dynamic predictions, where after observing each new observation, each new answer for a student, for example, we update the model and recompute the predictions. This corresponds more closely to practical applications, so one can argue that this is the more natural and correct approach. However, many papers are using this approach because it makes the evaluation easier, particularly for models where the updates of the models are computationally expensive. And again, the choice of the evaluation methodology can non-trivially influence the results, and it's important to pay attention to this aspect. So, to conclude, I would like to offer some of my comments on the progress of the field after the publication of the paper in 2015. These are clearly subjective notes, how I see it. My impression is that the choice of metrics now gets more attention than before. For example, it's more common, I think, to see usage of multiple metrics, not just one of them. And when there is a mismatch in the results between the different metrics, the researchers typically provide some commentary on the differences. However, the details on the rationale of specific metrics, specific subset of metrics, I think is still quite rare. Researchers typically do not provide arguments why they believe these metrics that they have chosen are relevant for the task that they are solving. And my impression is that there are still many cases where worrying usage of metrics persists, particularly in the deep knowledge tracing research. Many of the deep knowledge tracing research pay a lot of attention to the technical details of the neural networks that they are using, but then the evaluation methodology is described only briefly. They often use a single metric like the area under curve, to which I'm skeptical, and also the cross-validation methodology often seems to be simplified to fit the models, because the neural network models are often hard to train and update. So my impression is that the evaluation methodology often is done in such a way that it fits the model, but not the practical application where the models should be used. So I believe that there is definitely a scope for improvement and for more proper evaluations of this research. To conclude, I will just repeat the summary of the 2015 paper, which I believe is still relevant. I still stand behind my recommendations not to use that much area under curve, to rather prefer the root mean square error, and preferably to think more carefully about what is appropriate for a particular situation. And I definitely stand behind I think the general point that the choice of metrics deserves more attention is still valid even in 2026, or more generally that the evaluation methodology deserves more attention. Thank you and goodbye.